frequency spectrum of a sampled signal, total frequency, this one. Here x of f, here minus f of s, sorry fs minus fb 0, fb fs divided by 2 fs going up. This is the sampled signal frequency spectrum of the sampled signal. Sampling theorem historically attributed to the scientist Nyquist and the Shannon. Images. Let us assume we have a continuous distribution on a plane. Continuous distribution on a plane of values movements. More simply state an image. This is the image. In order to process using a computer, we have to reduce to a sequence number of means sampling to be reduced. There are several ways of sample an image or read its value, luminance, discrete points. This image. The simplest way is to use a regular grid with spatial steps x, y. Spatial steps x, y. Similarly to what we did for sounds, we define a spatial sampling rate. Sampling rate fx equal to 1 divided by x. Okay. As in the one-dimensional case, also for two-dimensional signals or images, sampling can be described by 3 facts and a theorem. Fact 1. The Fourier transform of a discrete signal is a function. This is called spectrum. Okay, of two continuous variables, omega x, omega y, these two, and it is periodic in 2 dimensions, into x, here, y, w. The Fourier transform gives back a complex number that can be interpreted as magnitude and phase translation in space of the sinusoidal component, such as spatial frequencies. Okay. Facts 2. Sampling the continuous space signal x of xy with the regular grid of steps. Xy gives a discrete space signal s of mn, x of x, mx, ny, which is function of the discrete variables m and n. Sampling continuous signal sampling. Okay, this is the sxy, x, y, s of s. Okay, with the regular grid steps, xy gives a discrete space of Sm1, discrete space s of m1, n. Sorry, it is not clear. Nothing but this one. S of m comma n equal to s of mx ny, which is the function of the discrete variables m and n. Fact 3. Sampling a continuous space signal with spatial frequencies fx, fy gives a discrete space signal whose spectrum is the periodic replication along the grid steps fx, fy of the original signal spectrum. The Fourier variables wx and omega y and omega x and omega y correspond to the frequencies in cycle per meter represented by the variables fx equal to omega x divided by 2 by x, fy and fy omega y divided by 2 by y. Figure 2 shows an example of spectrum of a two-dimensional sample signal. The continuous space signal had all and only the frequency components included in the central hexagon. The hexagonal shape of the spectral support region non-null spectral energy is merely illustrating the replicas of the original spectrum are often called spectral images, spectrum of sampled images. This is the sampled images, spectrum of the sampled images. Given above facts, we can have an intuitive understanding of the sampling theorem. Quantization. In the quantization, with the adjective digital, we indicate those systems that work on signals that are represented by numbers with the finite precision that computing systems allow. Up to now, we have considered discrete time, discrete space signals. If they were collections of infinite precision numbers, real numbers, number of this is a number of uniformly computers only allow represent finite subsets of rational numbers. This means that our signals are subject to quantization. So to be quantized. Sorry, quantized like this. So for our purpose, the most interesting quantization is the linear one, which is usually occurring in the process of conversion of analog signal into digital domain. If the memory word dedicated to storing a number of MAD of B bits, then the range of such number is discretized into 2B quantization levels. 2B quantization levels. Any value that is found between two quantization levels can be approximated by the truncation of rounding to the closest value. Figure 3 shows an example of quantization with the representation of 3 bits in 2's complement. Sampling and quantization of analog signal. The approximation introduced by quantization manifests as a noise called quantization noise. Often for the analysis of sound processing circuits, such noise is assumed to be white and decorrelated with the signal. But in the reality, it is perceptually tied to the signal itself in such an extent that the quantization can be perceived as an effect. To have a visual intuitive exploration of the phenomenon of quantization, consider the applet that allows to vary between 1 and 8 the number of bits dedicated to representation of each of the RGB channels representing color. The same number of bits is dedicated to the representations of an audio signal coupled to the image. The visual effect that is obtained by reducing the number of bits similar to solarizations. Solarizations. Basic relationship between pixels. Pixels. In digital imaging, pixel or picture element is a single point in a raster image. The pixel is the smallest addressable screen element. It is smallest unit of picture that can be controlled. Each pixel has its own address. The address of a pixel corresponds to its coordinates. Pixels are normally arranged in a two-dimensional grid and are often represented using dots or squares. Each pixel is a sample of an original image. More samples typically provided more accurate representations of the original. The intensity of each pixel is variable in color images systems. A color typically represented by three or four component intensities such as red, green, blue, and cyan, magenta, yellow, and black. The word pixel is based on contraction of pictures and EL for element. Similar formations with EL for element include the words voxel and texel. Bits per pixel. The number of distinct colors that can be represented by pixel depends on the number of bits per pixel (pp). A 1 pp images uses 1 bit for each pixel. So each pixel can be either on or off. Each additional bit doubles the number of colors available. So 2 pp image can have 4 colors and the 3 pp image can have 8 colors. 1 pp 2 power 1 2 colors monochrome. 2 pp 2 by 2 4 colors. 3 pp 2 by 3 8 colors. 8 pp 2 by 8 256 colors. 16 pp 2 by 16 600 65,536 colors high color. 24 pp 2 by 24 approximately 16.8 million colors true color. For color depths of 15 or more bits per pixel, the depth is normally the sum of the bits allocated to each of the red, green, and blue components. High color, usually meaning 16 pp, normally has 5 bits for red and blue and 6 bits for green, as the human eye is more sensitive to errors in the green than in other two primary colors. For applications involving transparency, the 16 bits may be divided into 5 bits, each of red, green, and available. This means that each 24-bit pixel has an extra 8 bits to discrete its blue, with 1 bit left for transparency. A 24-bit depth allows 8 bits per component. On some systems, 32-bit depth is opacity for purpose of combining with another image. Selected standard display resolutions include name, megapixels, width x height, CGA 0.064 megapixels, width and height 32 into 200, 320 into 200, EGA image 0.224 megapixels, width here 640, height 350, VGA 0.3 megapixels, 640 480, cross into 480. SVGA 0.5 megapixels to 800 into 600. XGA 0.8 1024 into 768. SGA 1.3